Hello, and thank you for joining this presentation. My name is Aditya Arora, and I'm presenting our paper titled Designing Sensory NIME for Autism, a design-led review and a synthesis of inclusive music interfaces tailored for sensory modulation and emotional regulation in children with autism spectrum disorder. This project was developed in collaboration with Erika Tandoori, Stuart Favilla, James Marshall across Swinburne and Monash University. Sensory dysregulation is among the most prevalent features associated with autism spectrum disorder, affecting over 95 of diagnosed individuals. These disruptions manifest as either sensory overresponsivity with heightened sensitivity towards light, sound, or touch, and underresponsivity, which presents as diminished reactivity or repetitive sensory seeking. Critically, these sensory challenges are closely linked to difficulties in emotional regulation, social engagement, and cognitive functioning. As noted by Kern et al., sensory difficulties are not peripheral but instead deeply shaped with autistic individual embodied with an effective experiences. Despite decades of clinical intervention, mainstream sensory therapies such as SIT, sensory integration therapy, and MSE's multisensory environments demonstrate inconsistent efficacy. This NITA trial, a major randomized controlled trial, found no statistically significant improvement in behavior compared to usual care. Moreover, existing therapies are often clinical driven, rigid, and environmentally static, lacking adaptivity and fluctuating sensory thresholds. This makes them difficult to personalize, especially for neurodivergent users with dynamic and situational sensitivities. In response, our study examines how NIME system, new interfaces for musical expression, may provide adaptive, inclusive, and responsive alternatives. We conducted a structured literature synthesis of 30 peer-reviewed NIME papers, ranging from 2015 to 2024, specifically focusing on those involving sensory engagement, interaction design for ASD, and adaptive multimodal feedback. A thematic synthesis approach was used to derive recurrent sensory principle across auditory, tactile, visual, and etc. domains, resulting in these three core and five design recommendations. Three emergent themes were: first, rhythm-based regulation. Many systems leverage rhythmic entertainment to support regulation and attention, with projects like Ollie, Musicane offering tempo-guided and immersive environment that synchronize neural and bodily rhythms. Theme 2, real-time adaptivity. Adaptive system using biofeedback and threshold modulation for environmental sensing adjust sensory stimuli, moment-to-moment mitigation, overstimulation, and preserving agency. Note examples include Snake Synth and Eardrum's Breath Sensor Piano. Theme 3, play-centered multisensory design. Interfaces like Westball and Boombox emphasize exploratory, non-goal oriented interaction. These promote engagement, agency, and meaning making through tactile auditory interaction and integration, making them away from compliance-based frameworks. Our synthesis generated 5 theme imperatives. First, in adaptive modulation, a system must dynamically adjust to ranging and changing sensory threshold in real time. Rhythmic anchoring, a predictable temporal structure, supports integration and internal regulation. Play-centered design encourages effective user-led exploration. Inclusive accessibility. Interfaces must be physically and cognitively adaptable. These findings form a sensory design heuristic for inclusive interface developed particularly relevant to NIME community. In alignment with these insights, we present Sonic Hue, a multisensory synthesizer, a MIDI keyboard for rhythmic input, 6 rotary knobs, and 4 arcade buttons for real-time modulation, Rainbow and MX patches for adaptive sound synthesis, a Raspberry Pi 6 running the audio engine, an Arduino controller managing external LED visual feedbacks, and future haptic outputs. Independent subsystems underpin the design, including adaptive profile switching, rhythmic co-regulation, modular controller, and a conceptual music decompression layer. This interface translates our research finding into a tangible tool for both autonomous and regulative and a co-regulative use. This work repositioned NIME system as therapeutically adjacent tool, not replacing clinical practices, but expanding the landscape of interaction for autistic users. We argue a shift from static intervention towards dynamic music interfaces, from behavioral compliances towards co-regulation and sensory literacy. Let the music become a language of regulation. We all invite you to read our full paper, detailed insight into all 39 systems, their gaps, design, and the full sensory design heuristic developed to support inclusive play-based interaction for neurodivergent users. Thank you.
Hi, my name is Ari Laloya, and this is a remote poster presentation for NIME Paper 208, Exploiting Latency in the Design of a Networked Music Performance System for Percussive Collective Improvisation. This paper and presentation document an experimental networked music performance system designed for musicians who are physically separated and dealing with significant network latency. Rather than viewing this as a problem to overcome, we embrace transmission delays as part of a novel musical strategy. We visualize all musical activity and explore complex cascades of musical responsibility beyond simple leader-follower dynamics, sonifying network characteristics, creating bilocated patterns where different musicians experience different musical outputs, and facilitating both live performance and composition support, or the opportunity to use material gathered from jam sessions in compositions developed asynchronously. So let's get into the details of this first point. Network latency and jitter scale up significantly with distance. This breaks down traditional real-time musical communication and makes certain kinds of rhythmic synchronization extremely difficult. Existing solutions include the laid-back approach, where musicians ignore latency effects, or follower-leader approaches, where only musical leaders experience two-way latency. Our system builds on the fake time approach, which can be applied to cyclical music. This technique adds extra transmission latency equal to one musical cycle, purposefully offsetting timing. The system implements three distinct user classes with specific musical responsibilities. Composers initiate musical activity by playing drums through keyboard presses. Performers respond to composer input, also playing drums but following along with incoming musical cues. Listeners receive the combined output from all performers, experiencing the final musical result. The system creates a shared visual space called the grid, where all participants see each other as colored nodes in a 2D space. Composers appear red, performers blue, and listeners are green. The setup process estimates latency between client pairs during initialization, then positions user nodes on the grid proportional to their network distance, making the abstract concept of network latency tangible and musically relevant. Musical interaction happens entirely through rhythm. Users play two different drum sounds by tapping either side of their keyboards. When composers play, circular hit markers traverse connections to performers, moving one grid line per beat. This creates a scrolling score that performers follow, and we can see this happening in the image below. When performers play, diamond-shaped waveforms ripple outward from their avatars, eventually reaching listeners who hear the resulting drum sounds, and we can see this happening in the GIF below. Listeners can move around the grid by dragging their avatars. This movement changes their timing relationship to different performers, letting them experience different rhythmic combinations of the same performance. Each position creates a unique temporal perspective of the combined musical output. Each performer hit marker arriving at a listener node triggers playback of a drum sound in their client. Differences between performers and listeners are quantized to beats, so each user hears a rhythmically coherent but differently delayed version of the combined output of performers based on their location, quote unquote. Listeners can learn from each other and make informed decisions about how to move based on each other's musical activity, the musical activity of other performers. At the end of a session, each listener's perspective, quote unquote, is converted to MIDI and made available to download, and these can be used as starting points for compositions developed out of time. Thus, the system facilitates both performance and composition support. I carried out an informal testing session with 3 distributed participants who met over a video call, had the project explained to them, we set up the server on a virtual machine, and a link to the client application was distributed via a chat. Data was logged in all 3 rounds and distributed as MIDI files. No issues were encountered when opening them in a range of digital audio workstations. I composed a piece of music asynchronously using the MIDI data from the session. A section of that piece will begin to play on the next slide, and you can read more about it in our paper, but thank you for attending this virtual poster presentation.
Our presentation is 2 sonification methods for the MIND-Cube, and we are from the Responsive Environments Group, MIT Media Lab. First, let me introduce the MIND-Cube. The MIND-Cube is an interactive device to help with gauging emotions. It is a tiny cubic fidget toy with different sensing modalities, including 4 tactile buttons, a rolling disc, a joystick, and a night-off IMU. The data collected by the MIND-Cube show different ways people interact with it and can infer different emotional status. The inside of the MIND-Cube is composed of 3 PCBs, a LiPo battery, and a linear vibration motor that can provide haptic feedback if needed. The data from all sensors is streamed through Bluetooth Low Energy. For this work, we are showing 2 different data sonification methods for the MIND-Cube: AI-generated music mapping and music mapping for expressive performance.
Our first mapping is an AI-powered one, which inversely relates to the sensor activity, generating loud, high-energy music when the MIND-Cube is not in use, and quieter, low-energy music when the MIND-Cube is actively being used. We built an architecture around the RAVE model, the real-time audio variational autoencoder, which was developed by Caillon and Esling in 2021. We use a model with 51 million parameters and with a latent dimension of 4. We train our specific RAVE model on the small subset of the Free Music Archive dataset. Then, we continuously generate 512 timesteps of RAVE latent codes through a latent diffusion model trained on the RAVE encodings of the same subset of the Free Music Archive dataset. We trained the latent diffusion model to generate latents conditioned on a specific RMS value, or root mean square, which encodes for the loudness and energy of the audio. By continuously reading the sensor data from the MIND-Cube, we are able to calculate a value which we use to condition our latent diffusion model via classifier-free guidance, and finally decode the latents to obtain an audio output. An entire pass through our architecture takes around 1 second to complete. To make the system reactive, we use outpainting to use an initial chunk of latents as a condition for the rest of the generation. Finally, we calculate our RMS conditioning value through this formula as a weighted average of the data readings from the input sensors. Let's take a look at the demonstration of the system.
Another sonification method is music mapping for expressive performance. In this method, we integrate the MIND-Cube into VCV rank using a custom-designed module that channels both trigger signals and sensor data. The trigger signals from the MIND-Cube are routed to multiple physical modeling modules, particularly mutable instrument clones like place and elements, where the active sound events and drive expressive synthesis. Meanwhile, the sensor data streams are fed into offset, scaling, and threshold modules to shape and normalize the signals before being mapped to control parameters such as timbre, morph, position, or brightness. Here is a short demo video.
Hello everyone, my name is André Santos and I'll be presenting the work I did under the supervision of Amilcar Cardoso, Matthew Davis and Roger Dannenberg called Tapping into a New Paradigm, a Synthetic Strategy for Automatic Drum Tapscription. Our motivation is simple. Test drumming is a form of tapping or drumming on a surface, often using the hands to create rhythmic sounds, and it is typically seen in informal creative contexts. However, very little work has been done to study or capitalize on this common rhythmic expression form. We consider rhythm-based interaction to be a promising area for exploration with several applications, such as percussive timbre transfer. To make the most of this interaction, we argue for a hybrid combination of symbolic and audio approaches. In this work, we focus on the symbolic aspect of this interaction and propose a new task, automatic drum tapscription. ADTS, or automatic drum tapscription, is a pun on automatic drum transcription. The task definitions are the same, with some slight changes. Drum tapscription is the task of detecting the positions in time and labeling the drum class of arbitrarily timbre tapped onsets in percussive inputs, assuming an underlying drum pattern. There are several new challenges regarding ADTS. Maybe the most different are the subtle intra-pattern timbre differences. Unlike real drum kits or even beatbox, each class is timbrically similar. Individual tap sounds, such as a tap kick or a tap snare, sound very similar in isolation. To illustrate this problem, we can look at this picture. Here we can see three different representations of the same drum pattern. On the bottom row, we have the MIDI information, color-coded. On the top row, we have the spectrogram for the corresponding drum audio recording, and on the middle row, we have the spectrogram of the corresponding tapped recording. We can clearly see that each class has a distinct frequency fingerprint on the original drum recording. That is not the case when comparing different frequency shapes for the tapped recording. Because of this, the spectrograms for each class across recordings is also very different. As there is a lack of a large aligned dataset that enables a traditional end-to-end deep learning approach, we propose a synthetic strategy to generate our own dataset. GMD, or the Groove MIDI dataset, is a dataset of drum patterns in both audio and MIDI format, first presented by Gillick et al. In 2019. We record a handful of tap performances while trying to replicate GMD's drum patterns. We call this our quasi-aligned, or QA, dataset. Then we process this dataset to obtain a collection of labeled one-shot taps. We explain this pipeline in detail in our paper. With this collection of labeled one-shot taps, we can then generate all of the GMD dataset, thanks to the MIDI information. We call the resulting dataset our synthetic GMD, or SGMD. Finally, having a large enough dataset, we train a temporal convolutional network on this dataset, using the original MIDI files as ground truth. For more details on the training and model, please refer to our paper. To evaluate our synthetic strategy and how well it can solve ADTS, we trained 2 more models for comparison, all with the same TCN architecture. First, we used the original GMD dataset as training data, effectively reproducing a traditional automatic drum transcription pipeline. And secondly, we use our QA dataset just to compare if our strategy improves results over an end-to-end ADTS strategy with a limited dataset. In this table, we present our results. First, we can see that the SGMD and GMD models converge well, contrary to the QA model. Then, SGMD is the model that generalizes best on real-world data. Models do tend to overfit their training data, as generalization remains difficult due to tap variability and synthesis artifacts. In conclusion, we introduce a new task called Automatic Drum Tapscription, or ADTS for short, which consists on a symbolic drum transcription from arbitrary percussive taps. We also propose a synthetic strategy to deal with the lack of a large enough dataset to enable a traditional deep learning pipeline. Results show promise, although generalization remains a hurdle, possibly because of a hidden discrepancy between synthesized and real data. To deal with this, future work may include data augmentation, such as reverb and noise injection, pitch shifting, and temporal jitter. And finally, reliable ADTS can enable controllable percussive timbre transfer downstream. Thank you for listening, and feel free to reach out if you have any questions or want to just chat about my work.
Hi, I am Alessandro Fiordelmondo. I will present the paper toward a repository template for music technology research. With this paper, we aim to contribute to the discussion around creating public repository to share research outcomes in the field of music technology research. And we propose a GitHub-based repository template intended as a guideline for building your own repository. Music technology research is a multi- and interdisciplinary field focused on developing new technology for music and sound, including software, hardware, and hybrid systems like DMI, as well as tools and datasets. These may be both the outcomes of research and the means for creating new musical works, experiments, or insights into sound and performance. The results are typically presented at dedicated conference or journal. Through this process, that we also build a critical discourse, the main track with which we can find and trace the values produced and developed by the research community. To support this discourse, publications alone are not enough. We also need softwares, documentation, datasets, and instruction, all materials that make the research reusable and expandable. Public repositories are the most common way to share and maintain these materials. The NIME community is already familiar with these needs, and discussions have been ongoing. An example is the NIME Hub workshop at the NIME2016, which focused on making repository use more systematic. And here, our contribution is to continue the discourse by proposing a repository template that could help researchers structure and share their work more effectively. First, we carry out 2 reviews to understand how repositories are actually used in NIME research. For the first one, we look back to 2001, the year of the first NIME conference, and we observe a clear increase in the use of repository over time. In particular, there has been significant growth in the use of the GitHub platform since 2008, the year it was launched. And in the second review, we examine how often repositories were created, shared, and reused during the last 3 NIME conferences. We found that repositories are actively used not only to publish new projects, but also to reuse those created by other authors. Based on these reviews and the idea that structured organization and clear documentation can improve and expand knowledge sharing, especially when it comes to software and tangible instrument, we propose a GitHub-based repository template. This template is intended as a flexible and adaptable tool to help make contributions in music technology research more consistent and easier to reuse. The MTR template is based on 4 essential actions, which are organize all material and documentation, provide information about the project and how to use the material, track change over time, and promote sharing and collaborations. To keep everything organized, we can divide the project structure into 4 main parts and reflect these in the root folder layout. So we will have software, the logical part of the project, including the source code, firmware, related files. We will have hardware, the physical part, with materials such as hardware design files, microcontroller specifics, and sensor information. Files, the knowledge part, which may include multimedia content, datasets, or similar resources, and documentation. GitHub discourages uploading large multimedia files, so we recommend using dedicated platform for storing these files and linking them back to the repository. Inform. GitHub offers several tools to provide information about your project. We recommend including at least a clear readme.md file in the root folder. This file should contain at least the abstract, the short description of the project, demonstration, with an image or a GIF showing how the project looks or works, especially useful for tangible instrument, technical notes, so key technical detail about the project, and instruction, a step-by-step guide on how to use the project. You can also add other useful sections such as contributions, listens, or how to cite. However, GitHub also supports separate files for including this kind of information. Keep track. We recommend tracking a project history using GitHub's tag feature, which allows marking specific point in the repository timeline to highlight key stages or versions. That can also be used to create releases, which are useful for packaging and sharing specific version of the software. Finally, to encourage sharing and collaboration, we suggest including 4 important files in your repository. Lessons, which define what others can and cannot do with the project. Code of conduct, which outlines expected behavior for participants, especially important in collaborative projects. Contributing, which explain how others can contribute to the project, and citation.cff, a file supported by GitHub that make it easier for others to cite the repository correctly. We can summarize the template as shown in the slide. Here, in these 3 QR codes, you can find the presented MTR template, the first one on the left, and then its application to 2 case studies, 2 original DMIs designed and developed by Patricia Cadavid, the Kipu, the center QR code, and the Yupana, the right QR code. We invite you to read our paper for more details, and feel free to contact us if you have any question. Thank you.
Q U I T K quick B R O W N Brown
B.
What you just heard was an excerpt of the rhythmic version of the pangram, "The quick brown fox jumps over the lazy dog," but in algorithms, a visual and musical system that turns each alphabet letter into a unique 4-beat rhythmic pattern using drum sounds, tone, slap, and bass. Algorithms is part of a larger system called Drumball, a tangible musical interface that lets young children interact with computers using rhythm and movement instead of screens and keyboards. The Drumball is at the heart of the Urban Griot Playground, or UGP, a curriculum and workshop series that combines culturally grounded design, body movement, and technology to help children and their families build literacy, social-emotional skills, and STEM awareness. This idea is inspired by a centuries-old tradition, the African talking drums, used to transmit language through rhythm. In 1981, Professor Nyangora Mbua from Côte d'Ivoire coined the term drumology, the study of drum language communication systems, and thus we honor that legacy with Drumball, combining tradition with modern digital tools. Our second generation prototype uses a custom fabric drum pad with conductive sensors overlaid on natural materials. We also created a tablet version that simulates a djembe drum as a digital game interface. Both versions turn drumming into letter making. How do you spell lion?
I-O-N
So what's the next letter here?
Oh. No, this is big. Wait, no. Yeah, and then
We piloted the drum ball in 2019 at a performing arts center with parents and children. Workshops included singing, dancing, drumming, and reflection on emotions, all tied to literacy tasks using the algorithm system. There were 3 major takeaways. First, early literacy skills. Children developed awareness of letters in print by manipulating symbols rhythmically, even without being able to hold a pen. 2, social-emotional growth. Children built emotional awareness and confidence by participating in group drumming, movement, and storytelling. And 3, engagement. Children were enthusiastic. Many expressed joy while drumming letters and playing language games, especially those struggling in traditional learning environments. Of course, we also faced some challenges, namely a small sample size, technical constraints, and durability issues with respect to the physical drum interface. Therefore, we created a more portable app version, but our long-term goal is to fully integrate the physical drumming with the learning software. We're now focusing on strengthening the design and improving evaluation methods to better serve this age group.
P. H.
A.
N. K. U.
Hello. In this video, I'm going to present our paper, AI Harmonizer, Expanding Vocal Expression with the Generative Neurosymbolic Music AI System, which is a project we've been working on at the MIT Media Lab. My name is Ansel Benchard, and my co-authors are Cameron Holt and Joe Paradiso. So a very common effect in vocal singing is harmonization, which consists of adding more vocals to an existing vocal melody line. So this can be done in partnership with other performers or through an external system, which allows a performer to harmonize their voice by themselves. So TC Alicon is the leader of Harmony Pedals, which the Harmony Singer, which is pictured here, is an example of. And it allows the harmonization of vocal lines by controlling the key of a piece with the guitar inputs. Jacob Collier, which is pictured on the right here, is famous for his use of his harmonizer, which is developed by Ben Bloomberg, and that he can control with his keyboard. All of these systems in general require an external input to control the key of the piece, and there are only limited work that focus on automatic vocal harmonization, and almost none of them are end-to-end ML-powered system, which is the one that we're presenting here. So let's go over a quick demo of the system.
So this is the AI harmonizer. So I can just sing or drag and drop one of my vocal lines into here, and this is how it sounds. This is a hyperparameter from basic pitch. It tends to work better at higher values if the melody is fast. So that's what I'm going to do. And we can just click convert. After a few seconds, we have the result. And this is how it sounds. Pretty cool.
All right, so the way our system works is through the architecture that's pictured here. So first, a vocal melody is passed through basic pitch, which is a model developed by Spotify that does automatic music transcription and allows us to get the MIDI notes that represent our vocal inputs. Then these notes are passed through an anticipatory music transformer, which is a transformer-based MIDI generative AI that's developed by Stanford CRFM, and that allows us to generate 3 different harmonized vocal lines for our melody inputs. Our vocal melody input is also passed through the RMVP model, which calculates the continuous F0 curve of our input signal, which corresponds to the fundamental frequency that's sung by the performer. This curve is then scaled based on the harmony lines that we generated with the anticipatory music transformer. Then we use the RVC architecture, which stands for retrieval-based voice conversion, to generate different vocal outputs for all of our different harmonies, and we merge them together to get our final output, which is our harmonized vocal melody. So the Antipater music transformer is a variant of the music transformer that was proposed by Thixton et al. In 2023. And we used a medium checkpoint, which is around 300 million parameters, that was pre-trained on the LAC-MIDI dataset for 800,000 epochs, and that's offered by the Stanford CRFM. Then we fine-tuned this base model on the JSB chorals dataset, which is made up of around 382 four-part harmonized chorals that were composed by Bach. We mapped the four voices, soprano, alto, tenor, and bass, to MIDI instruments 0, 1, 2, and 3. And we use the anticipatory music transformer because it introduces the anticipation mechanism, which allows us to set the entire melody line, soprano, MIDI instrument 0 here, as a control for the generation of the other voices. So once we have our harmonized vocal lines, we can use them to scale our F0 curve, which is extracted with the RMVP model. So as shown on the graph here, we first segment our F0 curve based on the MIDI notes of the MIDI melody, and then we scale each portion of the curve up or down based on the interval between the melody line and the harmonized line. And we use the formula that's shown on the right here. And we end up with 4 different F0 curves. Finally, once we have our different F0 curves, we can use the retrieval-based voice conversion model, or RVC, to generate the audio outputs that correspond to our different harmonies. To do so, we first pass our original melody line through the Hubert model to get a sequence of phoneme embeddings. RVC also uses an index file of existing phonemes that are extracted from a corpus of vocal lines sung by the original singer to ensure it can keep the original speaker identity. These phoneme features and the F0 curves are merged and encoded into a latent space, which we then pass through a normalizing flow and decode back to audio using hi-fi GAN, which is a vocoder that's trained on the original singer as well. We then merge our different audios to create the final harmonized vocal melody. And although our system does not work in real time, we're really working on speeding up the inference process. We show here the inference times of each step when running the system on an NVIDIA GPU and on a MacBook Pro with MPS support. Most of the gain could be achieved by speeding up the AMT inference, as you can see, and by performing the F0 calculation as part of the automatic transcription. So thank you very much. Please feel free to contact me if you have any questions.
Hello, my name is Vitor Pinheiro. I'm a master's researcher at the Federal University of Paraná and a practicing audio engineer and music producer here at Gramophone Studios. This presentation summarizes my NIME paper on a gesture-based system for the spatialization of sound objects in Dolby Atmos. Dolby Atmos has become a dominant format for audio delivery in many streams of music, cinema, and also live events. Yet, object movement is still very often programmed via mouse or by editing multiple automation lanes. These methods are precise, but they can become cumbersome when complex three-dimensional sound trajectories are required. The NIME community has introduced numerous spatial controllers over the last 2 decades, but many of them were tailored for very specific projects lacking scalability over a broader repertoire or cross-platform integration. This paper introduces a system that allows gesture-based control of spatialization within Dolby Atmos, currently a standard studio workflow. The aimed contribution is to bridge the gap between NIME's lineage and industry practices for in-studio applications. The hardware is a Leap Motion infrared sensor. Hand data is converted to MIDI control change messages by the Gecko utility. These messages are redirected through Mulligan to the Dolby Atmos Music Panel plugin in Pro Tools, giving direct control for the X, Y, Z, and size parameters. Spatial axes are mapped one-to-one with hand position, while hand rotation controls size parameter. Locating the sensor at desk height allows the engineer to remain in the reference listening position while performing gestures. A preliminary evaluation of this prototype was conducted during mixing sessions. As you can observe, the performed gestures were recorded to automation in real time, with the engineer having visual and auditory feedback. Some key advantages appeared during this experience. The first was the system's capacity for easily crafting fluid three-dimensional gestures in real time. Movements that once required separate automation curves for azimuth and elevation could now be captured via continuous hand gestures. Also, The size parameter, now accessible through simple wrist rotation, was used more often than on those sessions handled only with mouse and keyboard. Some constraints were also documented. Firstly, tracking dropouts during fast or occluded gestures, requiring post-session cleanup. Also, operator fatigue after approximately 1 hour of raised arm work. Some unintended activations happened when hands passed over the sensor. And lastly, the dependency on 3 separate software layers raised questions about obsolescence. We're now broadening the study to 5 professional Atmos mixers. The protocol will assess quantitative measures like tracing accuracy and gesture duration with semi-structured interviews on workflow integration. Further developments point to the possible integration of vibrotactile cues to improve spatial precision, as well as ergonomic studies to assess operator fatigue. In summary, this paper introduces a low-cost gesture interface that can be integrated into conventional Dolby Atmos mixing workflows. Real-time embodied control simplifies complex spatial movements, but ergonomic and reliability factors must be addressed before routine adoption. We welcome further discussion and collaboration. Thanks.
Hello, I'm Matthew Karen, and I'm here to talk about our project Melia. So, about a year ago, I made two observations. The first is that musicians love technological failure, and specifically the sonic and expressive possibilities that technological failure can afford. So we think of perhaps vacuum tube distortion in guitar amplifiers, or extended techniques on wind and stringed instruments that break the originally intended regimes of playing the instrument but offer new possibilities. But despite how much we love using technological failure musically, we haven't really yet found the canonical and expressive failure modes of AI and AI sound models and AI music models. Now, the second observation is that despite this, when AI audio models fail, they do so in a very unique and idiosyncratic way. And in fact, they sometimes do things that musicians do on purpose. So we think of, certain notes or pitches being held forever, which is, something we do all the time. We make all sorts of drone music and pedal points, or it might repeat a section or motif over and over again, which is, of course, something that composers and improvisers do regularly. So from these two observations comes the conceptual seed of this instrument, which is to train an AI audio model, in this case a pitch detector, a pitch shifter, and some filters, and to build an instrument around breaking it. In other words, we set out to build an instrument where the main expressive axes weren't the sound generation or controlling that generation, but actually the technology behind it, in this case an AI model, and how these sorts of AI models break. So the Melia instrument itself is in the form of a harmonizer, a digital instrument that kind of creates a choir out of your own voice. So you sing into a microphone and you play pitches on an associated keyboard, and pitch-shifted copies of their vocal input are generated that match the selected pitches that you are currently pressing on the keyboard. Now, before I explain any more conceptual or technical details, I want to show you all a video of myself actually playing Melia. But before I do so, I want to note a few things. First, the gap between what would be promised by a perhaps successful harmonizer, which simply sounds like several human voices, and the sonic complexity of what you will actually hear. That gap between the naively expected result and the actual result is what I believe we can reasonably label failure or technological failure. Second, that I am outside. The pitch shifting model that underpins Melia was trained on squeaky clean data from subtractive synthesizer patches, which means that the environmental noise of the outdoors is a very adversarial input. It doesn't know what to do with all these sounds like wind or birds or crickets. So especially note how those sounds translate to sparkly, suggestive, or unpredictable artifacts. So here we go.
Let's think aloud, and I say, think before the sky, rest before the dawn, and I say, before the sky, a rest before the dawn.
So I'm not going to get into all the technical details here. I encourage you to refer to our paper. But high level, we set up a signal chain of this trained pitch shifting model, several copies of it for polyphony, and then we break it in all sorts of ways. We add the adversarial inputs of the environmental noise. We deliberately induce bias in the model by giving it bias training data, causing some parts of the model or the filters to overfit. We add sort of bad or counterproductive heuristics to the pitch tracking model, so on and so forth. But beyond all the technical specifics, what I really want to focus on is this sort of high-level invitation that artists often find as much expressiveness using tools wrong as they do using them right. And the invitation, therefore, is to figure out how we can find similar beauty by using and abusing these new AI models in this new medium. So with that, I invite you to take a look at our paper. It is called Melia, an Expressive Harmonizer at the Limits of AI. I'm Matthew Karen. This work was done at MIT, but I will now be at Stanford. My email, mkaren@stanford.edu, is at the bottom. Thank you so much, and enjoy NIME.